In this video, we're going to take a look at something called solubility curves. We're going to learn how to solve problems with them and also see what they're all about. So solubility curve is a nice looking graph like this over here that shows you the solubility of a substance over a range of temperatures. And this one here has a whole bunch of substances on it. As you can see, different substances have different solubilities, meaning you can fit different amounts of different substances into a certain amount of solvent. Now, in this case, we're going to focus on our solvent being water. We're going to say this is how much solvent you can fit, how much solute you can fit in 100 grams of water or 100 mils of water. It's the same thing. 100 mils and 100 grams, same thing, because the density of water is 1 gram per mil. So if you have 1 gram of water, you have 1 milliliter of it, so they equate to each other. So for example, let's look at, choose one of these curves or lines here. It doesn't really matter which one. Let's choose this one over here, the KCl. If you were to follow this, you could find the solubility of KCl at different temperatures, meaning how much KCl could you dissolve in 100 grams at these different temperatures here. So for example, let's say I want to see the solubility of KCl at 10 degrees. I would go to 10 on my x-axis here, which is temperature, and I'd see the solubility of 30 because it reaches 30 here. So it means that at 10 degrees, I can dissolve 30 grams of KCl in 100 grams of water, okay? And then I could go ahead and do the same thing for another compound. So let's look at solubility curve for KNO3, for potassium nitrate. So at, let's say at 10 degrees again, its solubility is 20 grams per 100 grams of water. So a lower solubility than KCl. But let's keep looking at KNO3. Notice that as you increase temperature, solubility goes up. So at 20 degrees Celsius, the solubility is 30 grams per 100 grams. So you can do that for any substance that's here. And you'll notice for the most part, for these ionic compounds that are solids at room temperature, as you increase temperature, their solubility goes up. There is one exception, this one over here. Don't really worry too much about that exception. For the most part, you're going to see the ones that do go up as you increase the temperature. So your first skill should be able to explain what this graph's all about. So it's a solubility curve just shows you the solubility of a substance at a certain temperature in a certain amount of water, so or solvent. So 100 grams of solvent, for example. That's what our definition is there. And then your second skill basically is to be able to identify solubility at different temperatures. And then there'll be some math problems involved here as well. So yes, we're back to our math for grade 11 chemistry. So there's different points I want to indicate here first, and then we'll go in and do some problems together. So suppose you're looking at a point on a curve. So let's look at our KCl here. At 10 degrees, the solubility is 30 grams per 100 grams. So that's on this point here, that's your saturated solution. That's your saturated solution, okay, for KCl specifically. So for KCl, if we're at 10 degrees here, you can fit 30 grams in 100 grams of water. That's a saturated solution. But let's say you're at 10 degrees and you only put in 20 grams of KCl. Well, you could have fit more. So that means that your solution of KCl would be unsaturated. So the point on the curve itself is the saturated point. And then any less than that is considered unsaturated. Now let's say again, you're at 10 degrees for KCl again, ignore all the other stuff, KCl, and you somehow put 40 grams in there in your solution. You dissolve 40 grams. Now you're no longer saturated. You're above that saturated point. You tricked it to hold more, so you'd be supersaturated. Okay, so let's try another example here. So let's look at 20 degrees for KNO3. Okay, so for KNO3 at 20 degrees, you could hold 30 grams. So at 20 degrees Celsius, 30 grams dissolved in 100 grams of water is saturated. That means at 20 degrees, if you had 20 grams in there, you'd be unsaturated because you could still fit more. And if you had 40 grams in there, you'd be supersaturated because, well, you fit more than what you should have been able to fit. You tricked it to fit more in there. Okay? So understand that on the point, on the curve itself, that means saturated above is supersaturated, below is unsaturated for that specific compound or substance that you're looking at on your solubility graph. So this is the solubility curve here for sodium nitrate, for calcium chloride, for lead 2 nitrate, for potassium nitrate. You don't have to memorize these solubility curves, but you need to know how to use them. And you need to know the general trends behind them, that they basically go up as you increase temperature, with one exception, of course. And you can look up why this is an exception later on if you're really interested, because I know some of you are wondering, why? Why does this one decrease in solubility when you increase the temperature? And you can take a look at that on your own time and do a bit of research there to extend your knowledge of it. So we can solve some problems using the solubility curve using proportions. And so we can set up a proportion like this over here to figure out, for example, if we had different volumes of water other than 100 mils, how many grams of a substance we could dissolve in there. So you would set up your ratio where you have the grams from the graph over 100 mils of water, because 100 grams is 100 mils, is equal to the Y mils of water. So that could be, for example, in 200 mils of water, how much could I dissolve? So let me just do an example to clarify what I mean by that. So let's say, for example, I'm at 10 degrees Celsius. And at 10 degrees Celsius, I can dissolve 30 grams of KCl in 100 grams of water. The proportion should be the same if I increase the amount of water. So let's say I double the amount of water. I have 200 grams of water, still at 10 degrees. If I have 200 grams of water, I should be able to do not 30 grams, but 60 grams. So the ratio still maintains itself. That's why you can use proportions to solve problems using solubility curves. So let's go ahead and take a look at some examples of questions that you might see for solubility curves. So examples. Is a solution saturated, unsaturated, supersaturated if there's 50 grams of KNO3 at 30 degrees? And we are assuming I'm assuming in 100 grams of water, of course. Okay, so we're still assuming with 100 grams of water. I should have been more specific. So we're looking at KNO3 at 30 degrees, and we're saying there's 50 grams in there. So here's 30 degrees, and we want to see KNO3 at 30 degrees goes over here. So at 30 degrees, a saturated solution is about 45 grams of KNO3. And we're saying we have 50 grams of KNO3 dissolved in our 30-degree water. So here we have a supersaturated solution because we have 50 grams, which is more than the saturated 45 grams. So it would be a supersaturated solution. You can try the next one and pause it yourself. If the solution is a solution saturated, unsaturated, or supersaturated, if 5 grams of KNO3 are dissolved at 50 degrees. So again, you would look for your temperature, and you would try to find the curve for KNO3, which is about over here. So it looks like we're about 88 degrees for saturated. 88 grams for saturated. 5 grams is less than 88 grams, less than the saturated. So this means that we are unsaturated. You could fit a lot more at that temperature if you only have 5 grams in there. You're not even close to saturated at that point. Is the solution saturated, unsaturated, or supersaturated if there are 90 grams of KNO3 at 51 degrees Celsius? Okay, so 51 degrees Celsius, we're about here. Okay, 90 grams. So at 51 degrees Celsius, you can hold 90 grams, which is equal to the 90 grams saturation, right? It's on the curve. It's on that line there. So that means that that's equal to 90 grams at saturation. So basically, we're not overfull, we're not underfull or underfilled. We are just full, and that's our saturated solution. Now let's take a look at our next example here. So here we might need to use proportions. So 100 grams of water is saturated with KNO3 at 30 degrees Celsius. How much KNO3 will come out of the solution if the temperature is decreased to 20 degrees Celsius? Okay, that's an interesting one here. All right, so let's go take a look at our curve. We're told that we have 30-degree water and it's 100 grams of water, and we said that it's saturated with KNO3 at 30 degrees. So that means that if it's saturated at 30 degrees, we have about 45 grams there. So 45 grams of KNO3 is what can be held at 30 degrees. Now, if you decrease the temperature of water, theoretically, you should be able to hold less KNO3. And as a result, some of the 45 grams that's dissolved in there would have to come out of the water. So let's go take a look at the 20 degrees here. 20 degrees can hold 30 grams of KNO3. So what's going to happen when you decrease that temperature from 30 to 20, some of the dissolved KNO3 will precipitate out, will come out of the solution, because this lower temperature water won't necessarily be able to hold that in. And that's, of course, if you shake it up a bit or you add a crystal in it, it'll spit it out. So how much will come out? Well, if we had 45 in there at 30 degrees and we're at the 20 degree mark here, where we can only hold 30, theoretically about 15 grams of KNO3 will come out. It's the difference between the 45 and the 30. You can't hold as much anymore because you decrease the temperature, you decrease the solubility. What is the most KNO3 that can be dissolved in 250 mils of water at 45 degrees Celsius? So here is where you'd have to set up proportions. So let's take a look at 45 degrees Celsius. So this is at 45 degrees Celsius. If we had 100 grams of water, how much KNO3 could we hold in? And when I say 100 grams, I really mean 100 mils, because it's the same thing. So let's put in 100 mils here. How do I find this? Well, I can go to my graph. I can go to my graph and see at 45 degrees, how much KNO3 can I hold? So 45 degrees, and then KNO3, let's see, about up here, right? So that's about in the middle there, here. So about, let's just say around 75. Could be 74, but around 75 is what I can hold. So I can hold 75 grams of KNO3 at 100 mils. Now the ratio would maintain itself. So I'm going to equate this to 250 mils here, and I want to find what the value of X is. So the ratio should equate itself. So I can simply cross multiply to find out what X is. In other words, I can send this up here, and I can get that 75 grams times 250 mils. The reason this multiplies is because it was division on the other side. Divided by 100 mils should be equal to my X grams over here. The milliliters will cancel out, and grams will be left behind. And so my X is going to be equal to, we do our 75 times 250 divided by 100, and that's 187.5 grams. And if we, then we can put our therefore statement. So therefore, 187.5 grams of KNO3 will dissolve in 250 mils of water at 45 degrees Celsius. Now, theoretically, we'd have to follow our sig figs here as well. We only have 2 sig figs, so I would have to round this to about 190 grams. We round up, so that would be our 2 sig figs, like that. So let's try one more example over here. You can try it out yourself first, then pause it and then press play to see if you're on the right track. So a chemist prepares a saturated solution by dissolving 762 grams of solute in 876 mils of water at 20 degrees Celsius. So this is a bit of a thinker. We have 762 grams of solute in 876 mils of water, and that's the same thing as saying grams of water. And this is at 20 degrees. So essentially, let me ask you this. If I said I could dissolve 30 grams of a substance at 50 degrees, which substance is it? Well, you would take a look in 100 grams of water. I need to specify in 100 grams of water. You would look at the 50 over here and then see whatever one reaches the 30 over here. So this K2Cr2O7 would be our mystery substance. But that's if I specified 100 grams of water, okay? Now, here I didn't specify 100 grams of water, so I can't just go and say 20 degrees. Let's see where we reach, 762 grams up here, because that's not for 100 grams of water. But as you know, we can translate that into 100 grams of water by using our ratio, because the ratio should be the same. So let's basically say, okay, well, let's see what this substance would be in 100 grams of water as opposed to 876 grams of water. Again, mils and grams of water specifically are the same thing because water's density is 1 gram per mil. Meaning if you have 1 gram of water, you have a mil of water. Okay? So let's go ahead and make our ratio. So we said we have 762 grams of some substance in 876 mils of water. Now the ratio would be maintained if you had 100 mils of water, okay? And so I need to find what this gram value is there. So I'm going to cross multiply, and I'll get that X is equal to 762 grams times 100 mils over 876 mils. Cancel those out, and so you'll get 762 times 100 divided by 876, and you get approximately 86.986. 86.986. I'm going to put all my digits, 30137 grams in 100 mils at 20 degrees. So I'm not going to round this just yet. I'm going to go and just match this to whatever's on my chart. So I'm going to use this to match what's on my chart, 86.98. If there's no 86.98 and there's a 90, then I might go for that because I might need to round it to, actually I'd keep it to 3 sig figs in this case. So I'd be good leaving it at, for example, 86.98. That would round up to about 87.0. So 87.0 grams. So I'm looking for about 87, right? You're not really going to be able to see the difference between 86.98 and 87. So let's go ahead and look at 20 degrees and see what matches the 87 there. So here's 20 degrees, and we're going to keep going up until we get to that 87 point and see if there's anything that actually has that there. So we're about over here, okay? It looks like it could be 88, 87-ish. So it looks like therefore the substance is, as we mash up there, NaNO3, sodium nitrate. So you can solve a variety of problems using solubility curves, using proportions. You need to understand how to find the different temperatures and different substances that can dissolve in there. Remember, this is based off 100 grams of water. Different solubility curves might have different quantities there, so it's a good idea to read your y-axis and your x-axis as you do this. I would recommend you re-practice these problems just to make sure you understand them very carefully and know how to show your work in doing so. Just a quick little tip here. When we talk about the solubility curve of gases, it's a little bit different. As you can see, as you increase the temperature, the solubility goes down for gases, right? Because they tend to escape more and bubble out of the solution. So that's something we already saw before, but you can see that in the solubility curve of gases. We were looking at solubility curves over here for solids specifically, and we're looking at, for the most part, ionic compounds. But you can see that for the most part for them, their solubility goes up as you increase temperature, whereas for gases it's the opposite. And so one thing I asked you to think about in the previous video is, which one would go flat faster, warm pop or cold pop? And something would go flat if basically gas leaves it. So you have your pop here and gas starts to leave it. Which one would happen faster? And well, hopefully, or now that you know how solubility affects gases, you might say that the warmer soda pop should go flat faster. You see more bubbles over here because there's carbon dioxide coming out faster, since gases have a lower solubility in warmer solvents. Whereas in the cold pop, you don't see as much bubbling because the bubbles stay in, the gases stay dissolved, since you have a higher solubility at colder temperatures for gases specifically. And so that's a cool application of solubility of gases. And in the last video, we're going to take a look at supersaturated solutions. There's a demonstration you'll watch regarding how that works, and I'll walk you through how you would prepare a supersaturated solution.